Consider the cases of determinants of some special matrices. The first one, if A is orthogonal, then det A is equal to plus or minus 1. How can you believe it? How can you believe it? Look here. A is orthogonal implies A into A transpose is equal to I. Therefore, det A into A transpose is equal to det I. And previously we have forgotten to notice that det AB is equal to det A into det B. This is det A into det A transpose is equal to, what is the determinant of I? 1. Why? Because it is a upper triangular matrix or a lower triangular matrix, however you can call it. Product of diagonal elements is 1. But from the properties of determinants, det A is equal to det A transpose, isn't it? What is det A into det A? Det A whole square implies det A is equal to plus or minus 1. Det A is equal to plus or minus 1. This is the beautiful property of an orthogonal matrix. If A is orthogonal, then det A is equal to plus or minus 1. Yes, next one. Second one, if A is equal to I think you could have understood this. What does this representation stand for? What is this representation? This representation for a diagonal matrix, isn't it? So if A is equal to D1 diagonal D1, D2, D3, etc. Dn, we can understand this by the diagonal matrix D1 0 0 etc. 0 0 D2 etc. etc. 0 etc. 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 0 0 0 etc. Dn. No doubt it is again a triangular matrix, both upper triangular and lower triangular, of course. This also has its determinant as the product of diagonal elements, isn't it? Implies that A is equal to D1 into D2 into D3 into etc. Dn. etc. Dn. Good. Next. So I think there is no strain or pain to understand this. If at all there is a diagonal element, it is a diagonal matrix. If at all there is, the determinant of a diagonal matrix is nothing but the product of all diagonal elements. Okay then, next the third one. Suppose we have a scalar matrix 3 0 0 0 0 3 0 0 0 0 3 0 0 0 0 3. My dear friend, we are saying it is a scalar matrix, of course. Basically, it is a diagonal matrix, isn't it? Basically, it is a diagonal matrix. No doubt about it. As it is a diagonal matrix, what can you say about det A? Det A is equal to 3 into 3 into 3 into 3, etc. 3 to the power of 4. 3 to the power of 4. Why? Because, my dear friend, this scalar matrix A can be taken as 3i, isn't it? If you get 3 out from first row, second row, third, etc., isn't it? So it is 3i. Therefore, in this example, det A is equal to det 3i. Det 3i means this is a 4 by 4 matrix, isn't it? So it is 3 to the power of 4 into det I. What is det I? 1. Hence it is 3 to the power of 4, that is 81. Like that you have. So we have noticed that the product of, that is the determinant of a diagonal matrix is product of diagonal elements. Determinant of a scalar matrix is product of diagonal elements. Determinant of unit matrix is 1, of course. Product of diagonal elements is 1 in the case of a unit matrix, you see. Yes. And if A is an orthogonal matrix, then det A is equal to plus or minus 1. The next property, if A is involutory, if A is involutory, then that A is equal to plus or minus 1. You please recollect the definition of an involutory matrix. What is meant by an involutory matrix? A is involutory. What does this mean? A square is equal to I. A square is equal to I implies that A square is equal to that I. What is that A square? That A into A is equal to that I is 1. But you know that that AB is nothing but that A into that B. That is that A into that A is equal to 1. Therefore, that A whole square is equal to 1 implies that A is equal to plus or minus 1. Well, my dear, we have determinant of a matrix is plus or minus 1 in 2 cases. You please recollect the cases. Number 1, what is the first case? What is the first case? Orthogonal matrices. Second case, involutory matrices. Okay. So, in the case of an involutory matrix, that A is equal to plus or minus 1. In a similar fashion, if A is an orthogonal matrix, then also that A is equal to plus or minus 1. And next, if A is an idempotent matrix, then that A is equal to either 1 or 0. That A is equal to either 1 or 0. What is meant by that? And it is also a very, very simple proof. Within 1 or 2 steps, we will be having the reason. See, nobody is going to ask you to prove it, but you see, if you know the proof, the result will be remembered for so many days. Okay, look here. A is idempotent. What is the meaning of idempotency? A is idempotent. What is the meaning of idempotency? A square is equal to A. That A square is equal to that A. That A into A is equal to that A. That A into that A is equal to that A. If you get that A as a common factor, that A minus 1 is equal to 0. That A is equal to 0 or that A is equal to 1. One more familiar result is here. If A is an idempotent matrix provided A contains all real numbers as its entries, then only this becomes true. That A is equal to 0 or that A is equal to 1. Isn't it? So, it is a beautiful case to observe. If A is an idempotent matrix, then it is of determinant either 0 or 1. That is, if it is either it is singular or having a unit determinant. Having a unit determinant. Okay, this is about idempotency. Well then, next one. The next one, if next property, every nilpotent matrix is singular. Every nilpotent matrix is singular. To observe its nature and to agree with that statement, we must be able to recall the definition of a nilpotent matrix. What is meant by a nilpotent matrix? What is meant by a nilpotent matrix? If there is a positive integer n such that a power n is equal to 0, then a power n is equal to 0, then A is said to be nilpotent, and the least such positive integer n is of course called the index of nilpotency. And we are not interested about the index of nilpotency. We like to observe whether it is nilpotent or not. This is nilpotent. A power n is equal to 0. Therefore, det A power n is equal to det 0. Here by 0 we mean the 0 matrix. This is det A into A into A into A into A. How many times? N times. Determinant of a 0 matrix is 0, of course. Det A into det A into det A into n times det A power n is equal to 0. Therefore, det A is equal to 0. Det A is equal to 0. Therefore, every nilpotent matrix is singular, isn't it? Well done. Next one. Now let us recall some famous determinants. The properties of determinants is not yet over. While you go on, if you go on learning new concepts, meanwhile we shall be observing the properties of some determinants, and some new names also will be there. Look here. Let us look at some standard determinants. I think every one of you know this. This particular determinant we have come across in 2 or 3 different cases, in pair of straight lines, in conic sections, etc. Look here. This is nothing but ABC plus 2FGH minus AF square minus BG square minus CH square. The fundamental answer. How can it be? It's very simple. Come on. Let me expand the determinant in view of the first row. A into BC minus F square minus H into, why should I put minus there? I am doing about the first column, minus 1 whole power 1 plus 1, positive. Second one, minus 1 whole power 1 plus 2, negative. Yes, of course. Into, come on, remove the first row and second column, CH minus GF, isn't it? Plus G into the last row, the first row and last column, HF minus BG. HF minus BG. So that it is ABC minus AF square minus CH square plus FGH plus FGH minus BG square. Finished. This is ABC plus 2FGH minus AF square minus BG square minus CH square. This is a fundamental determinant. You might have recollected this. If ABC plus 2FGH minus AF square minus BG square minus CH square is equal to 0, then it is one of the conditions required for the lengthier equation AX square plus 2HXY plus BY square plus 2GX plus 2FY plus C is equal to 0 to represent a pair of straight lines. You see, if this particular determinant is not 0, then it may represent a conic. According to the conditions, if h square is equal to AB, then it is a parabola. If h square is less than AB, then it is an ellipse. If h square is greater than AB, it can be a hyperbola. Yes, such a famous determinant this is. Simply by looking at that determinant, you must be able to recollect this step. ABC plus 2FGH minus AF square minus BG square minus CH square. Isn't it? Simply by looking at it, you must be able to recollect this determinant. Well done. One more, some standard determinant. A, B, C, B, C, A, C, A, B. One of the standard expressions, it is, do you remember A cube plus B cube plus C cube minus 3ABC? Okay, let us have it. Come on. A into BC minus A square minus B into B square minus AC plus C into AB minus C square. ABC, ABC, ABC. So it is 3ABC. Minus A cube minus B cube minus C cube minus A cube minus B cube minus A cube. So it is minus of A plus B plus C into A square plus B square plus C square minus AB minus BC minus C. This is the famous determinant. If you have ABC, BCA, CAB as the three rows cyclically, then the elements of the three rows are in just like a cyclic expression, ABC, BCA, CAB. Then it is minus of AQ plus BQ plus CQ minus 3ABC. Suppose you interchange these two rows, ABC, CAB, BCA. Then it becomes AQ plus BQ plus CQ minus 3ABC. Well, next one. 1 omega square, omega square, 1 omega square, 1 omega. Where omega is one of the complex cube roots of unity. From the chapter complex numbers you could have studied. What are the cube roots of unity? 1 omega, omega square. After them, 1 is real and omega square are complex numbers. I think you can recollect the values also. Minus 1 plus r minus I root 3 by 2. Omega and omega square r. Okay, right. Such omega has been introduced in this determinant. What is the answer? It is surely 0. Why? Such a famous thing it is. Why is it 0? See, I am applying the row operation, R1 changed as R1 plus R2 plus R3. What happens? I like to change the first row. You add all the elements and place them in the first row. What happens in the first row? 1 plus omega square. Why is it 0? All the elements of the first row are zeros. As omega is one of the complex cube roots of unity, this is 0, this is 0, this is 0. This is the basic property of omega, isn't it? Isn't it? We can easily recollect it. So that 0, 0, 0, hence all the elements in the first row are becoming 0, hence the value of the determinant gets 0 as the value. Well done. Next determinant. One more determinant whose answer is to be remembered, or it looks very easy. Look here. Isn't it? Well, this is nothing but 1, 4, 9, 16, 4, 9, 16, 25, 9, 16, 25, 36, 16, 25, 36, 49. This is equal to the next one. 1, 4, 9, 16. C2 minus C1. What happens? 4 minus 1. 9 minus 4. 16 minus 9. 25 minus 16. Again. 9 minus 4. 16 minus 9. 25 minus 16, 26 minus 25, 16 minus 9, 7, 25 minus 16, observe all the columns, C2 minus C1, C3 minus C2, C4 minus C3. Actually, it must be done in 4 steps. I have done elements of second column, elements of third column, elements of fourth column are in AP. Again, 7 minus 5, 7 minus 9, 11 minus 9, 13 minus 11. 5 minus 3, 7 minus 5, 9 minus 7, 11 minus 9. And you just do not touch the first two columns. You just do not touch the first two columns. What is going to happen? The elements of third row and third column and fourth column are equal, since the answer is 0. So this looks so bulkier, but the answer is 0. But the answer is 0. So you remember that the big determinant is having a 0 value. It's a famous question. Another standard determinant, 1, 1, 1, A, B, C, A square, B square, C square. One, 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 A, B, C, A cube, B cube, C cube. 1, 1, 1, A square, B square, C square, A cube, B cube, C cube. These three look alike, but you see there is a slight difference. You please, I shall give you the answers for all these three determinants at a stretch at one time only. You please follow the answers. How do they change? Look here, this is equal to A minus B into B minus C into C minus A. In all these answers, A minus B into B minus C into C minus A is a common factor. Here, extra A plus B plus C will be remained, and here it is AB plus BC plus C. How to get it remembered? 1 into A cube, A power 4, this is a fourth degree. Therefore, 4 linear factors must be present. 1, 2, 3, 4. 1 into A square into A cube, A power 5, fifth degree. So it should have 5 linear factors, or 3 linear factors and 1 quadratic factor. Look here, A first degree, and this is of second degree. So total fifth degree is balanced, isn't it? Like that we should remember them. These are notable. I mean, what I mean to say is they are standard, popular, famous, that you must remember. Yes. And I like to give the proof for one of them. Shall we have the proof for the first one? The remaining two are absolutely in a similar fashion. We shall now try to prove the first result. The determinant 1, 1, 1, A, B, C, A square, B square, C square is A minus B into B minus C into C minus A. Okay? Come on. I like to start simplifying. LHS. Keep the first column constant, don't touch it. Second column, I am changing second column as C2 minus C1. 1 minus 1, B minus A, B square minus A square. Again third column, 1 minus 1, C minus A, C square minus A square. In the second column, you can have B minus A as a common factor, and in the third column, you can have C minus A as a common factor. What remains? First column, no change. Second column, 0, 1, B plus A. Why is it 1? We have pulled B minus A out. What is it, B plus A? It is B minus A into B plus A, and B minus A goes out, leaving you B plus A. Absolutely in the similar fashion, the third column becomes 0, 1, C plus A. Okay, this is therefore B minus A into C minus A into 2 elements are already made 0. Therefore, it is enough to find the cofactor of 1 itself, isn't it? Into 1 into C plus A, 1 into B plus A, B plus A. Therefore, C plus A minus B plus A. What happens? A will be cancelled. So inside the brackets, what is remain here? C minus B is remained. Now, this is B minus C. I like to write A in minus of A minus B. This is C minus B. This is C minus B. I like to write minus of B minus C. Already C minus A is present here. So total it is minus of minus is plus A minus B into B minus C into C minus C. Exactly in the similar fashion, absolutely in the similar fashion, you can have the other two determinants also. These are memorable determinants. S. Next one. There are so many other important determinants which shall be going through such determinants in due course of time very soon. Meanwhile, we have one more property of determinants in applying derivatives. What is that? Suppose f of x, g of x, h of x, p of x. There is a determinant. What is the derivative of determinant? He is asking us. How to find it? This is nothing but d by dx of f of x into p of x minus g of x into h of x. But this is f dash x into p of x plus p dash x into f of x minus g dash x into h of x minus h dash x into g of x. Of course, by applying product rule. You keep it at a side. Here we are lucky to have the 2 by 2 determinant. If at all there is a 3 by 3 determinant, it will be a tedious job, you know. So for that purpose, we shall now be obtaining a procedure. Look here, you obtain the process of differentiation like this. F dash x, g dash x. Don't touch h of x and p of x. Let them lie like that only. This is one determinant. And the other determinant is f of x, g of x, h dash x, p dash x. Come on dear, find the sum of these two determinants. F dash x into p of x, we have got, minus h of x into g dash x, we have got, plus f of x into p dash x, we have g of x into h dash x. So what can you understand? If a determinant like this is given, you find the derivative of all the elements or variables or functions which lie in the first row. Don't touch the remaining rows. You form one determinant. Plus, previously you have found the derivatives of those of first row. Now you give the chance to those elements which are present in second row for being differentiated. Okay, h dash x, p dash x. So instead of doing all these things, we can do directly like this. This is an illustration in the case of a 2 by 2 matrix. Suppose there is a 3 by 3 matrix like this. As we are supposed to adapt the similar type of a procedure. You can look at it. Consider the determinant f1 of x, f2 of x, f3 of x, g1 of x, g2 of x, g3 of x, h1 of x, h2 of x, h3 of x. We want to have the d by dx of this. You recollect the previous style, that is the style which we have adopted in the previous problem. This is now this sum of three determinants. What are they? Number one, f1 dash of x, g1 dash of x, h1 dash of x, f2 of x, g2 of x, h2 of x, f3 of x, g3 of x, h3 of x. Plus, now the process of differentiation must be applied to those functions which lie in the second row, because in the first determinant we have done that procedure for those elements which lie in the first row. Now the turn comes to second row. Come on, f1 of x, g1 of x, h1 of x, f2 dash x, g2 dash x, h2 dash x, and no question of touching this. You don't touch it. Let them be as they are. And of course the third determinant is plus. Now our turn is to deal with the functions lying in the third row. While producing that third determinant, we just keep the elements of first row and second row as they are. That is f1 of x, g1 of x, h1 of x, f2 of x, g2 of x, h2 of x, f3 dash x, g3 dash x, h3 dash x. This is the way in which we differentiate a determinant. We differentiate a determinant. Okay, you must proceed like this. Let us have one such illustration regarding this. This is the principle, rather procedure, rather pattern, whatever you call style, see. And applying this style, let us find the derivative of one such determinant. Now, that is the next question before us. You observe the question, how bulkier it is. Oh, it's a long determinant, 3 by 3 determinant having so many x's there, you see. One general student may feel like that. But you observe what is going to happen when you start it. F dash x is equal to 4x cube, 6x square, 6x, 4x cube, 6x square, 6x, 12x square, 12x, 6. Plus, now I find the derivatives of second row, elements of second row. X power 4, 12x square, 12x, 6. Plus, now the chance will come to the elements of third row. X power 4, 2x cube, 3x square, 4x cube, 6x square, 6x, 24x, 0. Come on, dear. The elements of second row and first row and second row are equal. So this determinant vanishes. Elements of second row and third row are equal here. So this determinant also vanishes. So the only determinant which lies before us is this. This is f dash x, you know. You need not obtain this determinant. You directly f dash 1 is equal to, now find it. 1 power 4. 1, 2, 3, 4. Isn't it? You find the determinant. It's not impossible. It's very simple. 1 into 0 minus 72 minus 2 into 0 minus 144. 3 into 48 minus 144. That is the answer, isn't it? So it is minus 72. This is plus 2 into 144 plus 3 into that. You simplify, you get the answer. You see, obtaining this determinant is somehow difficult when compared to that of this, isn't it? And you simplify, you'll be going to have the answer. Like that, we apply the process of differentiating a determinant. Suppose you have f of x is equal to g of x like this. What is the specialty of this determinant? Consider this determinant. In this determinant, we have elements of second row and third row are constants. Even if you apply the process of differentiating the determinant, the first determinant will be g dash x, h dash x, phi dash x. Isn't it? That's all. No question of having second determinant and third determinant. Why? Because these are constants. In the second determinant, second row becomes 0. In the third determinant, even if you apply the process of differentiating a determinant as we could have explained ourselves previously, the third row becomes 0 because these are also constants. Good. Like this we have. Yes. Suppose f of x is equal to 3x cube, 2x square, 5x, 9, 4, 5, 7, 8, 1. What is f dashed 1? Second row and third row are constants. It is just enough to have the derivatives here. What is the derivative of 3x cube? 9x square. If you put 1, 9. Derivative is 4x. If you put 1, 4. Derivative of 5x, 5. 5, 9, 4, 5. Oh, happy it is 0. Why is it 0? The elements of first row and second row are same. That is why it is 0. Therefore, in order to find the derivative of a determinant, it will be quite easier if only one of the rows contains variables or functions. If all the 3 rows are filled with the functions, then the derivative must be expressed as sum of the determinants. The number of determinants, such determinants will be the number of rows in the given determinant. That is the definition of f of x. Okay, this is about differentiating a determinant. Okay, then, if it needs you to integrate a determinant, then what must be the case? We shall be looking at. Suppose we have a function of this form. Observe the determinant. In this determinant, the first row is filled with some functions or variables like that, and the second row and third row are of course constants. In this case, if you want to have integral a to b f of x dx, then it will be integral a to b g of x dx, integral a to b h of x dx, integral a to b phi of x dx, a, b, c, p, q, r, That's it. Now you may get it out. If ABC are also functions, PQ are also functions or some variables, then what happens? Again, is it necessary to have the three determinants? I'm sorry. The process is not valid in the case of integrating. You must be able to have the determinant in terms of all these functions and then integrate it. Of course, if this particular determinant of definition of f of x contains two of the rows, what I mean to say is only one row is filled with functions or variables, then its integral can be evaluated like this. We shall now observe the determinant of a skew-symmetric matrix, which are all the different cases in finding the determinant of a skew-symmetric matrix. Such things we now come across. Look here. Consider the matrix capital A is equal to 0, 1, 2. Observe this matrix. Surely it is skew-symmetric, of course. It is skew-symmetric. What is both the determinant? That A is equal to that 0, 1, 2, minus 1, 0, 3, minus 2, minus 3, 0. Now you observe the matter. This is again 0, minus 1, minus 2, 1, 0, minus 3, 2, 3, 0. By what result, rather by using what result you are able to get this step? See, we know that det A is equal to det A transpose, isn't it? I have just considered the transpose of the matrix inside this. Now, you take a minus 1 from the first row, minus 1 from the second row, and minus 1 from the third row. What happens? Let us observe. Minus 1 whole cube into 0, 1, 2, minus 1, 0, 3, minus 2, minus 3, 0. What is minus 1 whole cube? Minus 1. So it is minus. What about this? It is just nothing but det A. Well, my dear, what is your observation? Det A is equal to minus det A we could have had. So x is equal to minus x happens when and only when x is 0, isn't it? Or you bring minus det A to this side so that we have 2 into det A is equal to 0 or det A is equal to 0. Do you mean that the determinant of every square matrix is, every skew-symmetric matrix is 0? No, here minus 1 whole cube is obtained as a common factor. As the number of rows is 3, minus 1 whole cube is obtained. If the number of rows is 4, then minus 1 whole power 4 might have come. Then it cannot become 0. The determinant cannot become 0. So by observing this result, we can say that the determinant of a skew-symmetric matrix of odd order can be 0. The determinant of a skew-symmetric matrix of odd order can be 0. Yes. Let us now verify it theoretically. Yes. By observing the previous example, that statement that we can frame is every skew-symmetric matrix of odd order is singular. What do you mean by singularity? When can you say that a square matrix is singular or non-singular? If A is a square matrix and det A is equal to 0, then we say that it is singular matrix. Otherwise, that is, if det A is not equal to 0, then the square matrix A is called non-singular. Well, what is the thing to be proved here, or rather verified here? Every skew-symmetric matrix of odd order is singular. For that purpose, it is a very, very simple proof that can be obtained within very few steps. Simple steps. Let A be an n by n skew symmetric matrix such that n is odd. Implies A transpose is equal to minus A, isn't it? From the very definition of skew symmetric matrix, we recognize that A transpose is equal to minus A because A is a skew symmetric. Well done. You consider determinant on both the sides. I have just taken the determinant on both the sides. Now you observe what is in left hand side. In the left hand side it is A transpose, det A transpose. We know that det A transpose is nothing but det A. And det minus A, how can you make use of that? Minus n whole power n into det A. How and why? Here we could have made use of one beautiful result. What is that? Det Ka is equal to k power n into det A, where n is the order of the square matrix and k is a known constant or scalar. Well, so that Ka is equal to k power n into det A, and of course in the place of k we have minus 1 here. Det minus A is nothing but minus 1 into det A, of course, minus 1 into A, of course. So in the place of k we have minus 1, hence it is minus 1 whole power n into det A. But n is odd. Therefore, det A is equal to minus 1 into det A. How? Since n is odd. What is minus 1 into det A? Minus det A. You bring it here. What happens? Det A plus det A is equal to 0. That is 2 into det A is equal to 0, or det A is equal to 0, implies A is singular. A is singular. Hence, we could have verified that every skew symmetric matrix of odd order is absolutely singular. What happens when n is even? Nothing happens. Same det A will be obtained. You cannot say anything particularly about that, isn't it? So, if n is odd, that is A is a skew symmetric matrix of odd order, then its determinant vanishes or it is singular. That's it about the determinant of a skew symmetric matrix of odd order.